Hello, I'm Keegan Williams. This is my Physics 2211 lab on motion of a falling object. So to understand this lab, we first need to know some fundamental physics principles. The momentum principle states that an object's momentum will change over time when a net force is present. The momentum principle can be rearranged to get the position update and velocity update equations, which will be implemented in the GlowScript codes to find the predicted position of the object in order to better understand the net forces on the system. We will also need the turbulent drag equation, which is the drag force on an object is opposite the motion and proportional to the square of the object's speed. Purpose of the lab in preview. So the purpose of this lab is to better understand the momentum principle in scenarios where the force exerted on the system is non-constant. Using the GlowScript code, we can model the motion of an object over time and analyze how the drag force changes the net force on the system as the speed of the object increases over time. After the lab, we will see that the experiment indicates how there is a change in momentum over time, which means that a net force is present on the system. We will also show how the speed of the object increases, the drag force will also increase. Between the drag model and the observed experiment, we saw a slight variation in the paths of the position versus time graphs, but they both showed that the object traveled the same distance. Here's a tracker video which shows our paper ball falling. So here's our free body diagram. The system for this experiment would be the crumpled paper ball, and everything else would be the surroundings, which includes the wall and the desk and the computer. After the ball is released, the largest net force acting on it is the force of gravity. As the speed increases, the drag force will grow in magnitude, which will decrease the net force on the object. So here are our initial conditions and code implementation. In both GlowScript models, the initial conditions are the same. The object was recorded to have a mass of 4.5 grams, and after the ball is released, we measured its distance from the ground, which was 1.66 meters. At the instant the ball is released, its initial velocity is 0. Over time, it will change because of the velocity update equations as the net force in the respective GlowScript codes exert a force on the ball. So here's how we implemented the momentum principle along with the drag force. So for the no drag force model, the motion of the ball can be modeled by simply using the weight force as the net force. As for the drag force model, we have to calculate the weight force and the drag force to obtain the net force. In the drag force model, the net force is equal to the weight force plus the drag force. Additionally, for this model, we found a b-value of 0.01035 as a good approximation of the ball's motion. After calculating the net force, we can use the position update and velocity update equations to track the motion and position of the ball over time. And to the left you see where I highlighted those parts of the code. Here's our GlowScript model, which shows our results for no drag. And here's our GlowScript model, which shows our results for drag. So for the experiment, we first had to crumble up a paper ball, and then we measured the height off the ground from which we were going to drop it. After dropping the ball from this height and recording the video, we uploaded to Tracker. In Tracker, we hand-placed coordinates of the ball as it fell, which created a table of data points. Using the mass of the ball, we had to calculate the weight force of the ball for both loads. To find the drag force, we approximated a v-value that aligned with the motion of the ball and used it to find a net force for the drag model. And here shows our differences between our observed and our models. You can see that for the no drag model, it hit the ground around 0.3 seconds before the other two did, which indicates that the drag model was a good indicator of the observed. Graph differences and possible sources of error. The key difference between the graphs is the time in which the object reaches the ground. In the no drag model, the object reaches the ground at 0.57 seconds, whereas the drag model and the observed reach the ground at 0.9 seconds. Additionally, while the drag model and observed reach the ground at the same time, their position differs by 1/5 of a meter halfway through the motion. So for sources of error, in our lab this may include imperfections in the recorded video and the coordinate placement, which has skewed the obtained y position. And additionally, there may have been slight rounding errors that accumulated over the course of the GlowScript code's iteration that may have made the model slightly inaccurate as it approached the ground. And using this information, we can likely attribute the slight differences in the position of the drag model and observed to the video imperfections and the accumulated rounding errors. Follow-up questions. So, from our experiment, we found that a drag model predicted the terminal velocity of the paper ball. Although it is atypical for an object to reach a terminal velocity over such a short distance, this is due to the geometry of the paper ball and its light mass, which caused a greater drag force to occur. And if the object was thrown downward, then its terminal velocity would be the same. As seen below, their terminal velocity stays the same, but the time to reach the terminal velocity would decrease since it starts closer to the terminal velocity. So in closing, we see that for some falling objects, the net force is non-constant, as it can change with the drag force on an object. As the drag force of the object increases, the magnitude of the net force on the object decreases since the drag force was countering the force of gravity. The findings of our experiment and our models reinforced the momentum principle, for we saw the object's momentum change over time as the net force changed. Additionally, the experiment supported the ideas presented in the turbulent drag force equation, which states that the drag force is equivalent to the square of the object's speed. In our lab, this is most readily seen in the rapid deceleration of the object, which is predicted by our drag force model. So, through this lab, we gained a deeper understanding of non-constant forces and how the motion of an object changes over time as the net force changes.